Welcome back to our series on probability theory. I'm Mark Ledbetter, and this is lecture video 15. We are going to talk about some special expectations in this section. And last section, we defined what the expectation was. The expectation of x, the expectation of a function of x. We talked about some properties of expectation, the expectation of a constant times a function, a linear combination, and we also introduced the geometric distribution with probability P of success. And last time we derived the mean and we just simply stated the variance. We're going to learn a new method of doing that in this section called the moment generating function method. And so let's give an overview of this section. We're going to define moments, which are related to expectation, of course, including central moments, which include our variance, the index of skewness, the rth moments, the moment generating function, as I alluded to, and the moment generating function technique for central moments, or for moments, yes. So let's say that our random variable x has a space, and we're calling it u1, u2, up to uk. And the probability that x, or random variable x, is equal to u sub I is f of u sub I. And that has to be 0 when u sub I is in the space. It has to be greater than 0. It's a positive number. And f of x is our PMF. Recall that the sum of f of x across all values of x is equal to 1. So because that takes up our whole distribution, and the total probability in a distribution has to be 1. And we recall that mu is equal to the expectation. So it's the sum of x times f of x across all values of x. And we can write that in this case as u1 f of u1 plus u2 f of u2 all the way up to, and I forgot, u sub k f of u sub k, and that is our expectation, which is our mean. Now, let's consider that u of I is the distance from the ith point from the origin to the ith point. That's the distance for u sub I. In mechanics, the product of a distance and its weight is called a moment. So u of I times f of u of I is a moment, and its moment arm has the length u sub I. And we call the sum of u sub I times f of u sub I the first moment about the origin. Now let's talk about a centroid, which is the first moment about the mean. So here we can think of this by about the origin. We mean something like x minus 0, sum of x minus 0, f of x. So if 0 is the origin, then x minus the 0 is, we're saying we're taking the moment about the origin, 0. Okay, here we're going to take it about the mean, because the mean is the center of our distribution, and it's where it balances, if you remember. Now, so we take the expectation. This is going to be the expectation of x minus mu. Okay? Oh, and I've written it here. That's right. And we can take the expectation of x minus mu, and it's an operator, a linear operator, the expectation is. And so we can break that up, e of x minus e of u. Well, mu. Well, mu is a constant. So that's just mu. And e of x is the mean, mu. So we've got 0. Mu minus mu is 0. And this is called the first moment about the mean, and it is always equal to 0. So let's do an example. Let's consider the PMF from example 1 in the last section. And it's f of x equals 4 minus x when x equals 1, 2, or 3. I want to take a moment and just say that these things go together. If you give me one without the other, you have not given me the distribution function. So the PMF the PMF is this whole thing. Please make sure you do that. All right, I do take off points if you don't include the space because it's really important. Okay, so let's get back to this. So E of x is the sum of x times f of x from 1 to 3. And so last time we did this, we found out it was 5/3. Now we're going to take x minus mu. Now we know that this is going to be 0, so let's see how it works. So x minus mu. Mu was 5/3, so we have for x equals 1, 1, and we have f of x 1, x equal to 1, and then 2, and then 3, and our probabilities that stay the same. And it turns out if we do our fractions, and you'll notice that I left these at the fractions alone, I didn't reduce anything, so it makes it easier to do this. Then we get up with -6 plus 2 plus 4, which is 0. 0 over 18 is 0. Okay. Now the second moment about the mean has a special name, and we call it the variance. And we use sigma squared for this. We also use the term var x, V-A-R, of x. And it's usually a capital V. Doesn't have to be, but it usually is. Okay, so E of x minus mu quantity squared. Now we do get sloppy with the notation here a little bit, but only in certain ways. So we could do this, but many times we'll just leave that extra bracket there off. And we know that we're taking the square of x minus mu. We're not doing that. That's a different thing. So we're not doing that. We're saying that we are taking the square of the x minus mu. So when we take this expectation, we can write it as a sum, x minus mu, f squared, f of x. And again, we call it sigma. And we're going to show that this quantity is equal to e to the x squared minus ex quantity squared. So these are two very different quantities. In fact, e of x squared is not equal to e of x squared, not unless the variance is 0, and that never happens. In real life, that never happens. Okay, so the standard deviation is the square root of the variance. The nice thing about the standard deviation is that it has the same units as the data, so the variance does not. It's in squared units. So now let's do this derivation quickly. So we've got sigma squared. We start off with what it's defined as, e of x minus mu squared. And then we're going to square this quantity, and we get x squared minus 2x mu plus mu squared. And now we distribute the operator, because it's the distributive property we talked about, a linear operator. And so we end up with ex squared minus the mu is a constant, 2 is a constant, and using our properties we proved in the theorem last section, we move the 2 mu outside, and we're left with e the x. And then we have e of mu squared, which is a constant. Remember that this is mu, so we end up with e to the x squared minus 2 mu squared, oh here it is, minus 2 mu squared plus mu squared. And we end up with ex squared minus mu squared, but mu squared is e of x, quantity squared. And there it is. Fairly simple derivation. Now, let's do an example. We're going to consider the PMF from example 1, and that was f of x equals 4 minus x over 6, x equals 1, 2, 3. So we want to find the variance of this. And this is e of x minus mu quantity squared, which is equal to e of x squared, and then the quantity e of x quantity squared. And we know that it's going to be mu for e of x, so mu squared here. And then we have our summation that we have to work out. And we figured out that mu was 5/3, right? Yeah, so 5/3. Now, so here we plug in each value. X is 1, 1 squared is 1, f of 1, 4 minus 1 is 3 over 6. Here we go. We plug in for 2 and f of 2. 3, f of 3. And then don't forget to subtract the square of mu. And so using common denominators, we end up with 3, and that's 4 and 2 is 8. 3 is 9 times 1 is 9. So that gives us, let's see, that's 12. That gives us 20 here. But over 6, we need a common denominator with 9. That's going to be 18. So we multiply that by 3. We get 60. We need to multiply this by 2 to get 18. So we have 50. So we end up with 10/18 or 5/9. The standard deviation is the square root of that. Okay. Let's do another quick example. Let's say that x has a uniform distribution on the first m positive integers. Find the mean of x. The first thing we need to do is write down the PMF. And if you remember, it's an easy one. It's 1 over m, and x goes from 1, 2, up to m. So the mean, E of x, is the sum of x times f of x. X goes from 1 to m, but f of x is 1 over m. 1 over m is a constant with respect to x. There's no x here, so we can pull it out. So we have 1 over m here, and then we have the sum of x from 1 to m, and we use our fact that is on our sheet. Whatever here is here at the top of the summation, the last number, goes here. So in this case, it's m times m plus 1 divided by 2. But this m and this m cancel, and we're left with m plus 1 divided by 2. Example 4, let's use the PMF and the mean of example 3 to find the variance of x. So this is for the uniform distribution. By the way, a uniform x is u1m if it's discrete like this, and for the first m integers. All right. Now, f of x again, here's our PMF that we've written down. We know that mu from our example is here, and this is in general for all uniform distributions u1m. So to calculate the variance, we need e of x squared minus mu squared. We have mu, so what we need to calculate is ex squared. That's the sum of x squared times f of x. F of x is 1 over m. Again, it's a constant, so it comes out to the front of the summation. And now we have the sum of the x squared, the first m positive integers squared. And if you remember from our formula, that's m plus 1, 2m plus 1. Again, we have an m here and an m here, so those cancel, and we're left with this quantity here for ex squared. Now, we have to take that and subtract our mean squared. So, to do this, what I'm doing here, what I did here was, let's see, so, all right, I didn't do much except just get a common denominator. So I got the common denominator, 12 is our common denominator, so here I multiplied by 2, and here I multiplied by 3 over 3. And so I end up with this expression. Now, you'll notice I have an m plus 1 and an m plus 1 squared. I factor one of those out, so it comes out into the front, and then I take the bracket, and I take what's left. That's a 2 and a 2m plus 1 on this side. That's a 3, and I've taken one of the m plus 1s, but I have one left. And then I multiply and subtract and simplify inside this bracket, and I'm left with m squared, m plus 1, m minus 1, and that's m squared minus 1, and it's all over 12. And this is the general formula you want to put on your formula sheet for the discrete uniform. So in our example, we plug in m was 3, so 3 squared is 9 minus 1 is 8 over 12. We will stop here and pick up in our next video. So let's move on down to here. Please remember to scan your lecture notes before midnight, of the date listed on the course calendar. Make them neat. They're for you. Update your formula sheet for your test and homework. Update any definitions, facts, theorems. Also, you want to update your list of distributions. So distribution list. If you have questions, come to my virtual office hours. If those just don't work for you, email me. I'm happy to help you. We'll see you.